Okay. So, today we are going to start the lecture on uncoupled motions. Okay. See, in the last class I derived or showed that equation of motion for an oscillating system for shape turns out to be of having a form something like mass plus some part into, well, I just put a simple this thing mode of motion b into z dot plus c z equal to f, where what I said is that this part, this was what was called as radiation forces. This part, this m z dot dot was mass inertia force. This was hydrostatic restoring forces. And this was wave exciting forces. Okay. And in specifically this could be called added mass force, and this could be called damping, but I think we will specify it to be radiation damping or potential damping force, because it is arising out of only radiation damping as we have derived earlier. Okay. Say let us call it damping, because other one also might look similar. Now, having said that, so this was single degree. If actually I consider a 6 degree of freedom, that is a ship in waves, then every motion will affect every motion and all these force get coupled, means you will have some radiation force arising in the heave direction because of roll motion, etc., etc. But today we are going to talk about that. We start with a simple heave equation of motion, single degree heave equation of motion. So, now that will look like the equation for that will have then m plus, let me call this Az now, now exciting force we wrote at F, but I explained to you that in waves, see, everything is periodic, okay, with a periodicity of omega e. So, therefore, this can be written as some amplitude of exciting force, let us say I call it this thing, and I can write it as cos omega e t. Well, we can also put a phase here, but that depends on, let me put a phase here also. Let us say we can also put a phase here as beta, because the phase you can also make it 0 depending on where you start from. Now, this is a single degree equation of motion for heave, when I will call this to be heave added mass. We can put it also Z here, and this is heave damping. And I also, let me put it Z also, that is heave restoring force. Now, before I discuss about these terms, okay, we will first let us talk about the solution of this equation of motion. How does it look like? You know, this is the equation of motion if the body is undergoing only heave and nothing else, and we are assuming that as it goes heave up and down, that is body is undergoing this mode of motion, it is not exciting or causing any other mode of motion, just uncoupled. You know, we are making this assumption. Now, you see, this equation of motion will start. Now, supposing we all know this, it looks like a vibration equation. If I made this 0 and if I remove damping, what I end up getting is what is known as undamped natural motion, okay, or equation for free undamped motion. So, let us look at that. So, if I just consider the inertia force and Cz z equal to 0, then this is what is my so called undamped free motion, right. Okay. Now, this undamped free motion has an a solution which will look like z equal to a sin omega z t plus b cos, actually either you call it this way or I can call it, well let me call it a1 b1, so that I can write it as a sin or cos omega z t minus beta z. As you know, it is the same way, either you can write in as a 2 sinusoidal term or 1 sinusoidal time with a phase gap. Okay, this is how the solution is, and the most significant thing here is Wz. This is given by square root of Cz by m plus Az, which is what is called natural period, natural heave period, sorry natural heave frequency. So that natural period is simply 2 pi, is going to be 2 pi by natural heave period, of course, I mean is implied here, by omega z. Now, natural period is very important concept. This is why we have to insist on that afterwards, but this we know, this is what is called, well we can also specify it is natural heave period for undamped motion or undamped natural free period. If you want to add the word undamped, we can also add that, because I have reduced damping, right, I do not have damping here. How does this solution looks like? Well, it will look like a sine curve. Okay. The beta is going to be a measure of this, that is the phase, this beta measures in some sense this how much later with respect to, well at t equal to 0 it is having a motion. Essentially, if I know A and if I know beta z, then the solution is fully complete, which means that in this equation, of course I am assuming we know m, az, cz. So here if I know, well if I know that I know omega z, so omega z is known, the only unknown is A and beta z, and of course I can always solve it if I have 2 initial conditions, but that is a trivial thing, not very important. Now coming to the next level, that is my damped natural period, free damped motion. If I consider, that means where I have a damping but no forcing. So here the equation will look like m plus az z double dot plus, so this is a solution. This solution we all know this, so we need not go through how. Nu t, we can call it d omega d, this is t t plus a2 sin omega dt, or which is equivalently e power of minus dt, I can call it this way, a sin omega dt minus eta, let us put something eta z d, let me just call it some phase angle. See, remember that any signal with a phase gap can also be written as sum of 2 sine, because you know sin a plus b is sin a cos b plus cos a sin b. If you actually apply, you will end up getting this relation. This is very straightforward. I mean, what I mean is that 2 sinusoidal curve is essentially 1 sine curve with a phase gap. If you add this up, if you add this and a cos curve, you will find out the summation is nothing but another sine curve starting with a phase gap. So, one can use either this expression or this expression. Okay, I mean, so this is interchangeable. We need to know that there are two unknowns in the signal, A1, A2 or A and eta z, two unknowns whichever form you write. So, this is known. In this case, this signal looks like that, this part is a free vibration, but there is a decay part. Now, this nu is given by B by Bz by 2 m plus Az. This is called the decaying constant. In fact, this solution that I wrote, we have made an assumption here that Bz is small, decaying constant is small. See, if the decaying was very high, then it would have just died down aperiodic motion. But in a, it is presumed water is a very less viscous water as such, even if you take viscosity. Damping, of course, here we are not considering even viscosity, then the damping is very low. As a result, Bz is always very small, or Bz by this nu is very small. So, it is always looking like that. So, this is a relevant solution for this as far as Heave equation of motion is concerned. Of course, the other thing is Wd. This is given by that this is a damped period frequency z square minus nu square root over. Now, here or therefore, I have got Td equal to 2 pi by omega d. At this point, so this is how, this is the solution. How does it look like? It will look like decaying. This is my z, this is my t, and this decay is e power of minus nu t. Depending on this nu, if it is larger, it will decay faster, longer. This part, this is decay parameter, right. What is this? As we have found out, this is actually my b by bz by 2. I just wrote it in last slide. So, this is a decaying parameter. Okay. Once again, if I want the solution, very simple, I have two unknowns, because the solution that I looking back at that, two unknowns, one was you can call it either this and this or this and this. Okay. If I know this, this and this, the solution is like this, the solution is fully known. If I could determine these two unknowns, I can determine these two unknown if I have two conditions, such as somebody says, let us say that I have got initial condition, say let me put it this way. That is A1, A2 or A and eta zd as this one, as I mentioned, and for that you need two conditions. So, we can put in form of initial condition. For example, I can say that for example, let me see. I can say that at t equal to 0, my z equal to za, and also t equal to 0, my z dot equal to 0. That is very actually very valid point. What I mean is that it is something like you are pushing the body down. So, I know at t equal to 0 what is my, see I pushed it down to an extent za. So, I know what is my initial displacement, that is what is at t0 z is how much. I pushed it down, no imposed motion, left my hand. So, at that time my initial velocity, that is z dot, is 0. So, I know this, for example. So, if I know this, I can find out C1, C2. I give an example of that. See, if I look back here again, I will write it in this form. in C1 C2 form. Let us say if I wrote z as again e power of minus nu t a1 cos omega dt plus a2 sin omega dt, I have z dot given by minus nu e power of minus nu t. This becomes minus a1 sin omega dt plus a2. So, I know that see at t equal to 0, z is equal to, from this equation C1, from 1 I will get z is equal to simply a1, right. You see, because at t 0 this is 0, this is also 1. So, z becomes a1 cos 0, that is a1, and which of course is equal to my za, because this is my initial condition. So, za becomes a. Which one? Oh, okay, the omega d will come, right, that is what you are saying, trying to tell. Yeah, okay, see here your omega d will come, right. Oh, okay, sorry, yeah, you are absolutely sorry, yeah, absolutely. So, we are going to get actually, yeah, right, this was actually for this differentiation, then I am going to get one more term, that is e power of minus nu t, right, I am sorry about that. We are going to get here, well, let me actually deduct that, okay, wait, let me write it now, you are absolutely right. So, this is, I am sorry, this is going to be first minus nu e power of minus nu t, then a1 cos omega dt plus a2 sin omega dt, right, plus e power of minus nu t. Here I am going to get this differentiation, that is what you are saying, right, that is minus we are going to get a1 omega d into sin omega dt, right, plus here we are going to get a2 omega d into cos omega dt, that is right, you are absolutely true. So, in any case, what therefore is happening from this one, obviously at t 0 my z dot becomes this goes off, then my z dot will become minus this a1, right, plus I will end up getting omega d into a2. Okay. So, this becomes my one equation and this becomes another. So, from there, and this is actually equal to, in my initial condition is 0. So, I end up getting 0 equal to this. So, my point to say here is that I have found a1 as z1 and here I have got 0 equal to minus nu za plus omega d a2. So, this gives me a2 equal to nu za by omega d, right. Really speaking, this I just went through this, it is very trivial. My full point of saying here was that we had two equations, sorry, one equation with two unknowns. So, to solve that I need two equations. So, to get the two equations I need two conditions, it can be any two condition, I can say any two condition, so that I can get two independent equations. So, this is once you know the two equation you can solve for it, that is all. Really it is also not very important, it is just to prove the point, but what is most important for us now is the forced part, the full solution, that is now we will look at forced damped equation of motion, the final one. So, here I have got let me call it here f, well, let us call it f0 here. this is E. Now, this has, everybody knows this, it has two, its solution can be written as a sum of the free that so called complementary solution and the full solution. So, it essentially the solution can be written as Z equal to e power of minus nu. One is solution for the homogeneous part, that is when you make it 0, and one is for the full part. So, this is something like, or A1 let me call it. Now, here will come an interesting part. Plus there will be a sinusoidal solution, force solution E t minus say epsilon z. Now, you see how does it look like? The first one is this one is going down like that, and the second one is actually a force solution of omega t. You are actually adding the two to get the solution. Now, the question is that what is our interest? Our interest is obviously in only in this part. Why? Because you see, given sufficient time, this thing will decay because of new factor. So, essentially if I were looking at a steady state solution, that means if I are holding for a long time, what would happen? The body will begin to heave only with this oscillation, forced oscillation, because this one will decay down. In fact, the full solution may look like if you were to draw experiment something like that, and ultimately it will become a straight line. So, this is what I am looking at, this is what is my interest fully. So, we are looking at only the steady part of the solution. Again, here my unknowns are this and this, and what you notice here is that this is oscillating at that exciting frequency omega e. Yes.
So, that assumption that T will be very large is true for maybe an offshore structure?
No, not at all. All structures, see, the question is this decay, we are not talking of true or see the question. It is nothing to do with structures here. It is that we are looking at a.
When we are talking about a ship, the whole period might not be that long.
This is a decay factor minus V by A. Okay, when minus V by A would make e power of omega t small. If t in fact in real life just 1 minute will become 0 actually, because see you are having e power of minus b by 2 A. Okay, this factor whatever way it is with t, if you give t 1 second, 2 second etc., very shortly it becomes 0 in practically. In fact, in reality it will become actually, you won't even notice it, it will be actually 0 in almost like 3-4 periods, 10 second, 15 second or so. Remember, it is nothing to do with structure, it is connected to the decay part of it, and we are only looking at the steady part of the solution. When we are saying forget ship or offshore structure, even offshore structure, when the wave comes I am looking at for 1 hour, 2 or 3 hour kind of solution, not in 10 seconds that goes off. And second thing is that wave are always existing, you cannot actually fix the time when it started, when you are looking at that. See sir, suppose you go today on board, well it has been oscillating yesterday onwards, it is not that it has started 0 calm sea and suddenly started. So, what you see is always a steady solution, the decay part is just not there, and simulation also shows. In fact, we will see later on by numbers b by 2a that how fast it decays. Okay. Now, we will look at this steady part solution, and that part of solution of course we know it. So, it turns out that the solution for this steady part again from vibration is given by like this, Z A is given as Z static into this solution, when Z static is known as static heave amplitude. Well, we are calling heave amplitude, but what I am saying is a typical solution for a vibration, forced vibration equation. This will be F0 by Cz. This is a solution. Mu z is this all we all know it. That's why I will not going to go through this in the solution part. What we need to know in this course is to tell the typicality of heave motion. you know, like how does it heave, how much it does, etc., etc. Well, because this part, anybody who has studied you know, any vibration system mechanically will find out. Standard things, and the other thing is this epsilon, right, what we wrote epsilon z. Now we have to write the kappa part. Okay. And of course, I missed out here one, that is this part, this is given by it is called non-dimensional damping factor. See, what I mean here is that solution for this equation is fully known to everybody. Okay? It is, you can write it this way, let us look at the diagram, that is more revealing. So, it will look something like this. If I were to look here mu, this is here nu equal to omega e by, this is always easier. Actually what we are plotting is z versus omega. Okay. Now you can write this in z versus omega e we want to write. Instead of omega e we are writing a non-dimensional form of omega, that is omega e by omega z, and instead of writing z we are writing mu, because z is mu into zst. Zst is a constant. So, it is the same thing. This way it is easier, this becomes something like that. It goes to actually let me write etc., where this is for damping 0 and this is increasing that is damping. This is actually 1 magnification factor. See, the thing is that again, okay, let me put it this way, this is actually 1 undamped 1 and this is actually the damped 1. See, what is happening, understand this, all of you have seen this, what does it show? It shows that this equation, that if I have this body here heaving, okay. Number 1 is that at low frequency, very low frequency, my we need to see this very important, you know, at low frequency, at the limit of omega tends to 0, my magnification factor is 1, which means it simply goes up as f0 by what, c. At this low frequency. Okay. At this region, first of all, if I had no damping, I would find out that at tuning factor of omega e by omega z, my magnification is theoretically infinity. But if you give a slight damping, it will come down to finite value. As you keep giving more damping, it actually the peak shifts towards this side, lower side, because this corresponds to omega d. Okay. The damping natural damp period. You go down this side here, it will eventually come down asymptotically to 0. Okay. Now, the important point of this, we all know this, you see, this part is known, but what we want to know is not the solution per se, importance of the solution with respect to heave motion. Remember this equation mx dot dot plus bx dot plus cx equal to f, it is actually this vibration equation, everybody have studied it, it is ubiquitously occurring in nature, any oscillating system, this is the phenomena, string vibration, any vibrating system, even atom vibration, whatever. The question is not in the solution, all I showed here is a typical solution which also all of you know very well. What is important is that the characteristic of that with respect to heave mode of motion, that is very important. In heave, see, heave is not going to be like atom oscillation, it is not going to be like a string oscillation. What is that special like characterizes the motion? So here I want to tell you this, see, look at this low end, what the low end means. Now let me took another picture then. Now omega e tends to 0, what does it mean? It means very long wave, okay, infinite period. So you have this very long wave, the body here. Now we will again write down the equation of motion. Well, I just now z, you can write z as za. Well, now this time I am going to write the sort of e power of minus I omega e t. Let me write it this way, okay. But there is also e phi, maybe e power of minus I beta, or no, I what we call epsilon in the real. Let me call e power of minus I. I used the term earlier. Let us see the phase. Phase was used as epsilon z. So we will use as epsilon z. Okay. This is not important really speaking. But what I mean, I wanted to add this. Now you see z dot is going to be proportional to minus I omega e into this thing, and z double dot is proportional to omega square in e into this. What I want to say, velocity has a proportionality of omega e multiplied by displacement. Acceleration has proportionality omega e square. Now when omega e is very small, okay, omega e is very small, what would happen? Obviously, so this equation will look like minus omega e square into something za minus I omega e into something plus you can say cz into z equal to f. Now it will look something like that. Okay, let us pay attention on that. See, the first term, the force, the added mass force is in proportion to omega e square. Second term, damping, is in proportion, of course forget the phase gap, in proportion to omega e. Third one is not, is a constant. Now when omega e tends to 0, this will actually have no influence, very less value, this also will have very less value. So my z becomes simply f by cz, that is what has happened. Now what is cz? We will come to that, but what it means is that it is happening so slow, in fact we will find that the phase also, phase gap becomes 0 with respect to exciting force. This will simply go up and down with the water, means if water goes up, body goes up, water comes down, body comes down. It will simply ride the wave by hydrostatic force. So that means every time if you stand here, you are going to find your water surface or freeboard same, the freeboard is going to remain same. You don't even feel that you are moving, because first of all it is moving very fast. So that is what has happened in tsunami type of wave, very long wave. You don't even know that there is a wave coming, because you have actually just gone up and come down with the water. So as you stand, you always look at the water, you don't feel you are moving. First of all, omega is small means Te is very large, so it takes all the time. Just imagine it takes 10 minutes to go up 1 meter, so how do you feel it? So this is one extreme of this graph, this part, and we can call this region to be hydrostatic motion. That is, this side of motion is dominated by hydrostatic force. It is a hydrostatic force that dominates. You can make all kind of mistake in Az, Bz, does not matter, don't even bother. Very low frequency, the body is going to go up and down. So I can make 100% error in Az in estimation, does not matter, I still get a good estimate. This is why the small boats in large wave simply ride the wave. So, this is what we call hydrostatic dominated motion. Now, coming to the other side, then now this is this side now also we have to see. Now, let us look at this side, high frequency side. Now, here again if I look at this equation, see it was omega e square into something, that is my inertia force, plus I omega, see it is minus here, into something plus C z into something equal to force. Now, you see when omega is very high, okay, high frequency, motion is very fast, what happens? This becomes a much more dominating force. Okay. This also becomes fairly dominating force. This becomes comparatively less important. So, what happens is that it becomes inertia dominated, and you will find out that the force of this and force of this is opposite in sign. As a result, there is a phase gap. I did not put the phase gap, but if you are to put a phase gap between that, theoretically there will be a change of 90 degree here, the phase gap. Okay. That means, look at this, earlier I had got Cz into something is f, now I have got minus omega square minus something into Za equal to f. Obviously, the Za in this case, if it was like that, in the other case it is going to be just the opposite. So, what is happening? This is very important. In this case, in the first case my boat was riding this, but now in the lower end my boat is out of phase with that. That means, when the wave is rising, it is sinking, is more dangerous. You see, that is what I wanted to tell you from physical point of view. That means, if I were to draw this here, now in this case when the water is rising, my boat is sinking. Here when water is this thing, my boat is rising. So, you see, I end up getting an oscillation related to the water surface much more pronounced, which is of course more important, because what happens, just imagine this case, free surface is rising, the wave is crest, but my ship is going down. So, there is a chance of water, my freeboard is reducing. So, inertial dominated motion typically have a response which is out of phase with the forcing of the wave, typically. Okay. Now, the third thing that is important is the other part, that is damping part. Now, this part. Now, this part, this small part here, this values, peak value depends purely on B or nu K value. K is nothing but damping. You will find out that if you give K 0, it is infinity. If you give K to be 0.001, it will come down to final value drastically. So, this is extremely sensitive on damping. So, this part, inside part, what we can call damping dominated motion, but it is very small part only, because really speaking, estimating this amplitude requires a good estimate of damping B, very good estimate of damping B, and damping is always very difficult to estimate, but we can call it damping dominated. And in fact, that is theoretically this is where there is a change of phase of that Ez value. Ez value actually undergoes a phase change in this case. So, this is the kind of modes of motion that we find. So, we will find out therefore that you see three cases. One is high frequency wave, there is a, it is going like that, it is in this case sinking more, in here rising more, this gap is changing. Go to this long wave, it is always riding the wave, is always having the same. That means, this freeboard part remains constant, more or less constant. So, and it is very easy to study this motion, because I do not have to actually determine Az, Bz, etc. Again, if I were to look at this equation of motion, in fact, what would happen is that that even this part, this has got two parts. Actually, this was, if you know inertial parts, and I said that in the first class, it is incident wave and the scattered wave together combine and gives this Fe, in principle. Now, at very low frequency, the body is going to disturb the waves very less. So, scattering also is very small, because very long wave, the body simply goes up and down. Since it goes up and down, it is not like diffracting, or it is not going to disturb the wave field. Even if the body was not there, wave looks exactly the same. So this becomes very small as such, because this is also proportional to omega e actually. So you end up getting only this part, very easy to find out, very easy to figure out, no problem at all. And let us say you are doing a solution, you made a mistake in this estimate, which is of course very usual to do, because hydrodynamics is on this and on this and this. So in a static dominated force, there is no hydrodynamics practically. You can make all mistake in hydrodynamics and you end up getting a good estimate. In an inertial dominated force, which happens to be more critical in some sense because there is a out of phase, you unfortunately required to have a good estimate of this force and this force and this force, because it is the hydrodynamic forces that decide inertia dominated motion, and it is inertia dominated motion where typically I have a tendency for free body to change. So therefore this is a situation where things that is critical, my demand on calculating AZ, BZ and FS dynamics correctly is also become more important. See, had it been opposite, that the critical scenario I have less hydrodynamics, I could have afforded to have bad or poor estimate of hydrodynamics, but this is a situation here that you cannot ignore hydrodynamics. Therefore it is the hydrodynamic forces that are more important for inertia dominated this thing, and also for damping, if you look at that, for damping part. Okay. So this part is extremely important for us to understand. So again, if I were to look back this, I will just draw it again here, a typical this. Okay. So this, once again I call this ZA equal to something, right, like ZA equal to mu into, well, ZST, and I plotted only mu here. Whichever you plot, mu becomes 1 means it is a hydrostatic force, etc. So this H lower frequency range is, once again I tell you, hydrostatic dominated. This side inertia dominated. This is damping dominated, but this can be narrowed down to a small part, this damping. Now you tell me, we will try to tell from physical point of view what is the importance. Now look at that. Typically you will find out, or we will find out afterwards, from the point of view of wavelength. What is the wavelength in open ocean? We have seen it may be something like maybe 50 meter going to say 500 meter, okay, something like that. If you look at that, it will be of this range. In fact, lambda by L, if L is ship length, may range some value depending on the L, of course. Now what happen is, if I take a boat, small boat of 30 meter or 40 meter, let us say 50 meter boat, then all the waves that existing would appear to be long with respect to the boat, because lambda by L smallest is 1 and goes to 10. Okay. So relatively what would happen, the boat will have a tendency to follow the wave. So mostly if I have a small boat, then we are looking at always relatively high frequency motion. Why I say relatively? Because again this response will depend on, remember, omega E by omega Z. So omega Z comes in picture, omega Z of course will become low, this I will come later on, but let us say that if the shape is this, and if the waves are much longer with respect to that, you expect it to go up and down. But if the shape is much longer with respect to this, then obviously what happens is that you have a situation where you have got essentially a relatively high frequency wave. Now I can relate omega E is lambda. Remember, omega E can be related to omega gk lambda. So omega E can be related to omega wave, can be related to lambda of wave. So I have omega E is lambda wave by L shape. So I can somehow this make it in order of this. I can relate that in some sense. It is order of wavelength by ship length. Now what is happening? Obviously, when wavelength by ship length lambda by L is actually lambda is small, it is small, means omega E is high. When lambda is larger, long wave, means omega E is of course small, period is large. That is what typically is the question of lambda by E. Now, you see, for a given lambda, if L is small, then obviously what would happen? If for a given lambda, if L is small, this value becomes large. So that means small ships feel the waves to be large. Large ships will feel the wave small. Now, going by the open ocean 50 to 100 meter wave, 500 meter wavelength, obviously what happened, if a 50 meter ship feels 500 long ship as 10 times its length, but a 500 meter long ship or a typical 200 meter long ship, a ship typically we have got say 100 to say 300 meter. Ocean goings are something like that. A typical ocean going ship is something like 100 meter, 200 meter, 300 meter. A VLCC may be of this range, a typical small cargo ship also of this length. So, for these ones, obviously what happened, say 300 meter long ship, there are waves which is 200 meter, that is going to be small, and therefore, for actual practical ship we are in this region for large ocean going ships. You see, I cannot avoid studying hydrodynamics. I am trying to emphasize the importance of that if you look at large ocean going ships, okay, then large ocean going ships would encounter waves where the encounter frequency is moderately high and therefore inertia force dominates. As an example, you will find out this example, you ever go to port, you will find out there is a large ship. If you will see that there are some small ripples, and I used to always wonder personally myself that in such cases the boat does not even move up and down. You think that, and there is a small boat next to it, you will find out as if the boat is grounded. I used to feel wondering that this boat seems grounded, these waves are flashing by and the ship does not move. A small boat here is sloshing up and down. Okay, so that means what, this is so small, it is actually so high frequency, the inertia in fact it is something like this region for this boat, that it does not have any force to move up and down at all, but slightly more and something like that, this will now begin to move up and down. And of course, in open ocean these things always happens, and in this case these motions are this region, we are shifting to this region. Remember, for a 300 meter long ship to go to this region I need 1 kilometer long wave, that means lambda by L to be 3. If L is 300 meter, lambda is 900 meter, but most lambdas in open ocean are 300, 400 meter itself. So, I end up getting lambda by L to be around 0.75, 1.5 type, and in such cases I have inertia domination. So, my point of saying is that large ocean going waves, you cannot avoid studying dynamics, and in order to get dynamics now I have this problem of having to estimate the dynamic part of this part I have to estimate to some moderately acceptable degree. In the other case I could ignore it completely, I can even make it 0 or some very rough estimate. If I made 100% error in that, I might have made 5% error in the estimate of motion in the low frequency range. But here if I make 100% error, I might make 50% error in my motion. That is very important. That tells us that added mass damping and exciting force becomes an important parameter for us to study. We just cannot avoid it. Okay. Now, just last few minutes of this class, let me talk about this natural period. Okay. Cz, well, omega z equal to root over of Cz by m plus Az. To do that, I first need to have an estimate of Cz. What is Cz? I will talk about that, but before that let me tell you the difference between omega z and omega d. See, omega d is omega z square minus nu square. Nu is b by m plus Az 2. This nu is a very small number. Typically for water, it is not water is not like thick oil. Water is one of the least viscous thing. of course, there is no viscosity also, and this is actually radiation damping. What is the origin of that I will tell later on, but in next classes when we discuss B and A. But what I want to say here is that this is small. So, this is small means this square is even smaller. So, suppose it is 0.1, this becomes 0.01 say numerically. Then what happened, omega d is approximately same as omega z. So, in all practical purpose, when we study natural period and we say resonance, as you know that when omega e is omega z, it is resonating, what we call, that is this peak value. So, we can estimate the resonance by simply taking omega d to be as omega z. So, our importance become omega z rather than omega d, which is also very useful for me, because if I had to do omega d, I had to get nu means I had to know bz. Bz is much more difficult to estimate. So, therefore, let me talk about this. This is very important, because if my omega e happens to be this, I am going to have a very large heave motion, right. So, natural period becomes a very important point, especially for offshore structure. An offshore structure, it is digging oil from somewhere, always stationary. If it begins to heave very large, you might stand here and not feel, but this oil, this line is going to have this tension. So, you actually cannot allow or cannot have oil exploration going on if the heave exceeds some value, say 3 meter or 2 meter or something like that. So, if it is heaving very largely, you actually end up having this problem. So, heave becomes very important. When will it have large? If the natural period meets the exciting period, remember. So, natural period becomes very important, very important from the point of view of study. Now, for this I need this. Now, what is CZ? We will now try to tell about that. You see this CZ, and I will just, okay, I think that we will talk about this CZ tomorrow's class, because we do not have time, but we understand here one thing is that CZ is hydrostatic restoring force. So, it comes purely from hydrostatic, there is no hydrodynamics. Having said that hydrostatic, it is not exactly the buoyancy force, which is what we will try to find out. It is the unbalanced hydrostatic force. And remember that we have always called hydrostatic force Fs as something into Z, and this something is this Cz. So, we will derive that Cz expression tomorrow, so that we can estimate these values for practical structures and figure out which range they are. Then we will find out very ironically that it turns out for typical ships, omega z is actually in the range in which oceans exist, waves exist. Okay, so, or is it? All right. So, we will get back to that tomorrow.